Today, we are going on one heck of a journey. We're going to follow a single sound wave from the outside world through this incredible labyrinth inside our heads, all the way to the point where it becomes, well, an experience. Let's get into it. But let's start with a question that I think we've all asked ourselves. You know the feeling, right? You hear a recording of your own voice and you just cringe. You think, there's no way. Do I really sound like that? Well, stick with me because by the end of this, you're going to understand exactly why that happens. All right, so our journey begins where the physical world first makes contact with our senses. We're starting right at the outer gates, the part of the ear you can actually see, where these invisible waves of pressure first come knocking. And the hero of our story? It's the sound wave. Now, that might sound complicated, but really, it's just a vibration. A ripple of pressure moving through the air, kind of like a ripple in a pond. That's it. And our entire auditory system is designed to catch and make sense of that simple little vibration. So you look at the outer ear, the auricle or pinna, and you might think it's just kind of there. But it's actually a beautifully designed funnel. Its whole job is to catch those sound waves and guide them down the ear canal. And get this for a cool fact. In the embryo, that whole complex shape grows from just 6 tiny little bumps called auricular hillix. It's an incredible piece of biological origami. Okay, so our sound wave has traveled down the ear canal. Now it's about to enter a totally different environment, the mechanical world of the middle ear. This is the amplifier room, and this is where things get a massive power boost. So why do we even need an amplifier? Well, the middle ear is here to solve a big physics problem. See, our sound wave has been moving through air, but the inner ear is filled with fluid, and trying to push a vibration from air into fluid is like trying to yell at someone who's underwater. Most of the energy just bounces right off. The middle ear's one critical job is to crank up the volume on that vibration, so it can make a splash. And how does it do this? With the 3 smallest bones in your entire body. But here is the absolutely wild part. Millions of years ago, these tiny, delicate bones that you hear with, they used to be part of your ancient ancestors' jaw. I'm not kidding. You are literally hearing with your old jawbone, and you can see just how deep this connection is right here. When we're developing as embryos, these little bones, the malleus, incus, and stapes, they come from these structures called branchial arches. The first arch, the one that forms our jaw, also makes the hammer and the anvil. It's just a stunning piece of our own evolutionary history written right into our anatomy. But wait, the middle ear isn't just an amplifier. It's also a bodyguard. It has this incredible built-in safety feature called the middle ear reflex. It's a totally involuntary system designed to protect the really delicate parts of your inner ear from getting blasted by loud noises. So how does it work? Well, when a really loud sound hits, we're talking over 70 decibels, 2 tiny little muscles spring into action. The tensor tympani pulls on the eardrum, making it tense. At the same time, the stapedius muscle pulls back on the stapes bone. Together, they stiffen the whole system, acting like a shock absorber and dampening the sound by as much as 30 decibels. It's your body's own automatic volume knob. Okay, our journey's taken us through the amplifier. Now we enter the weird and wonderful world of the inner ear. It's this fluid-filled spiral where the real magic happens. This is where a physical push gets translated into the language of the brain, electricity. And this incredible conversion process has a name: auditory transduction. It all goes down inside this amazing, snail-shaped structure called the cochlea. Inside, there are these highly specialized cells just waiting to perform what is basically biological alchemy, turning a physical vibration into a pure electrical signal that the brain can actually understand. The tiny heroes that pull this off are called hair cells, and they come in 2 flavors. You've got your inner hair cells. Those are the primary sensors. They're the ones that hear the sound and send the main report up to the brain. But then you have the outer hair cells, and these things are just something else. They're a living amplifier. They physically move, they dance, they contract and expand to boost soft sounds by up to 40 decibels. They don't just listen, they actively sharpen the sound. Absolutely incredible. And there it is. The electrical signal is born. The message is ready. We've officially reached the final stage of the journey. The signal now travels up the auditory nerve and enters the brain itself, where it's finally going to be decoded and turned into a rich symphony of perception. So that electrical signal, it doesn't just go to one place. It races through a whole series of processing hubs in the brainstem. You can see the pathway here. It's like a relay race, where each stop on the line analyzes the signal in a new way, checking its timing, its loudness, its pitch. This whole chain of command ensures that by the time the information gets to the cortex, it's already been processed and is ready to become what we experience as sound. Now, out of all those stops, I want you to pay special attention to one in particular, the superior olivary complex, because this place is a huge deal. This is the very first spot in the entire brain where the information coming from your left ear and your right ear finally meets. This is where true stereo hearing begins. So what does the brain do with that combined information? It uses it to pull off two amazing tricks to figure out where a sound is coming from. For low-frequency sounds, it calculates the interaural time difference, basically which ear heard the sound a few milliseconds before the other. For high-frequency sounds, it uses the interaural intensity difference, which ear heard it louder, because your own head actually casts a sound shadow. Your brain is doing these near-instant calculations all the time to build a 3D sound map of the world around you. We've done it. We've followed that vibration all the way from the air into a complex pattern of electricity in the brain. So now, with everything we've learned, we can go back to that original mystery and finally get our answer. Why does your voice sound so weird on a recording? And here it is. When you speak, you're actually hearing your own voice through two separate channels at the same time. You've got air conduction, which is the sound traveling through the air and into your ear canal, just like any other sound. But you also get bone conduction. The vibrations from your vocal cords travel directly through the bones of your skull to your inner ear. And that bone conduction path carries a lot of lower frequencies, adding a richness and a bass that only you can hear. A microphone? It only picks up the air conduction. So that strange, maybe higher-pitched voice you hear on a recording, that's the real you. That's how everybody else hears you, all the time. Which leads us to this final, really profound idea. Sound as we know it doesn't really exist out there in the air. That's just pressure waves. The experience of sound, of music, of a loved one's voice, of the wind, is a detailed, rich, beautiful simulation that is constructed moment by moment entirely inside your brain. And so that leaves us with one last kind of mind-bending question to think about. If this entire complex reality of sound is a construction project happening inside our heads, what else about our world is being built for us by our own minds? Thanks for joining us.